colleagues from Institute of Physics of Materials in Brno, Czech Republic, and Karlsruhe Institute of Technology, Germany. Yeah, so I'll just briefly speak about why this particular topic is need to be studied, the material will be studied, testing equipment, and the testing conditions, then jump to the results, and finally sum it all up. So, well, besides the obvious advantages of 3D printing, such as the freedom of design or waste minimization, there are several issues which needs to be met, such as the issues related to fatigue and what's actually going on in the material when you're subjected to fatigue. Real components are, however, also subjected to variable temperature fields, which is why also studying thermomechanical fatigue is of high importance. In my eyes, fatigue of 3D printed materials is an area which is still hugely unsatisfyingly unexplored. So, we study 316L stainless steel with a chemical composition shown below. The material was supplied in printed bars, which were annealed for stress relieving. The technology which was used for printing was SLM, selective laser melting. The specimens were printed either in vertical or horizontal building direction. That refers to the loading axis, basically. We have the experimental setup here, and we see that the specimens, as they were cylindrical, means that the vertical building direction were aligned parallel to the loading axis, whereas in the case of horizontal, it was obviously 90 degrees to it. The machine we used for testing was the electric testing machine from Zwick, or by Zwick, for temperature, for varying the temperature field, we used induction heating, copper wire, and we cooled the grips with water, and of course the specimen was also naturally cooled by thermoconduction. So regarding the testing conditions, the cycle time was 60 seconds, which means we had 30 seconds compression to 30 seconds of tension. Half cycle, we tested the specimens in the range of 550 to 750 degrees centigrade, and the tests were controlled with mechanical strain, total mechanical strain amplitude. In case of in-phase tests, the strain amplitudes were 0.2, 0.3, 0.5%. In case of out-phase tests, it was 0.3, 0.5, 0.6. For those of you who might be unfamiliar with what in-phase, out-phase means, so basically this chart shows it. Yeah. So if we go up with the temperature, we go into tension. In case of in-phase, in case of out-phase, it's just the opposite, which means that okay, if we go up with the temperature, we go down with the stress, which means we go into compression. Yeah. So the maximum compression coincides with maximum temperature in case of out-phase. Yeah. So, to the actual results, now let's take a look at these CT scans to see what the defects were like. Interestingly, we found no Lego fusion defects in the frame of experimental resolution, which was around 5 microns. So if there were any smaller, we didn't see that. Probably not, since Lego fusion defects are usually quite large. There were just few round defects which are supposed not to be as bad, let's say. Okay, we also location arrangements in dislocation cells, which were elongated in one oval direction. The black dots you see here are oxides or oxynitrides rich in manganese and silicon, which
the yellow ones.
Cool. Interestingly, or importantly rather, the oxides were distributed randomly.
Oh.
Cool. Okay, so now let's take a look at some charts. So here we have. Here we have cyclic hardening and cyclic softening curves. So generally, just to take it briefly, in case of in-phase tests, we saw cyclic hardening for the first 2 cycles at maximum, which was followed by gradual softening until fracture. In case of out-of-phase tests, in both building directions, we saw initial period of cyclic hardening up to 5 cycles, which was followed by again, a rather short period of softening for about 30 cycles, which was followed then by saturation of cyclic stress response. In some cases, there was even slight hardening present. Yeah, so if we compare it with the conventional material, in this case, rod 304L steel, which was subjected in somewhat similar temperature range, we see that in their case, in the case of conventional material, the initial hardening period is also short, but not so short, let's say. I'll later explain why. And also the stress response was after that saturated, in both in-phase, out-of-phase testing conditions. Okay, so from the lifetime curves, it is quite noticeable that in-phase was apparently more damaging than out-of-phase testing conditions. Another features we could deduce from the charts are that regarding the vertical building direction, as we see here, given plastic strain amplitude, it leads to longer lifetime comparatively to horizontal building direction. Yeah. From the cyclic stress strain curves, we can deduce that horizontal building direction was, on the other hand, linked with notably higher stresses and lower plasticity. Another thing we can notice is that in outer phase, should we test it in outer phase in stress cycling, we would get higher lifetimes for horizontal building direction. Okay, so now let's see what the actual mechanisms are like. Yeah, so first let's take a look at in-phase tests. Here we have fracture surfaces which show numerous flat facets which are somewhat connected through small transgranular bridges. Yeah, but however, the damage character in general was mostly intergranular, which is kind of typical for in-phase tests. In these pictures, we see what the damage mechanism was like. Yeah, so there was extensive internal damage, and the mechanism was of Greek origin. Yeah, so we had, it's clearly seen in the picture B, we had nucleation, growth, and coalescence of the cavities along grain boundaries. That was the primary damaging mechanism in phase test in general. Interestingly, the dislocation structure remained almost unchanged. It was very stable. Yeah, the cells were still elongated in one direction. The qualitative difference you could notice was that, okay, there were more dislocations, obviously. Yeah, here it is how it looks like actually in TM. So yeah, it was pretty stable. The only new feature were these guys, these small particles which were rather flat and elongated, which nucleated along grain boundaries. I will later get to what these might be like. Ah, yeah. So that's it. Yeah. So we did some EDS mapping, which, by the way, also proves what I said before, that these round particles are oxides. Where is the oxide? Are oxides or possibly oxonitrides. With the nitrogen level, I'm quite cautious because it's EDS and it's okay. It's also So one might be true, might be not. And these guys along the grain boundaries are first of all rich in molybdenum, kind of depleted from iron and nickel, but interestingly they are not rich in chromium, which you would expect in steels. Yeah. Usually chromium and molybdenum as ferrite forming elements segregate together, make carbides or whatever. Okay. I also included this picture of sulfur. This is rather confusing. It's probably misleading because the characteristic X-rays of sulfur and molybdenum overlap. Yeah, so I do not believe this. Sulfur is just not there. Okay, now let's take a look what the damage mechanisms were like in out-phase testing. So it was different. Obviously, we had multiple fatigue rate initiation. The damage was mostly transgranular, and there were striations present. Yeah, you can not so well see, but they are in there. You have to trust me. Surface cracks were running approximately perpendicular to the surface, which is also clearly seen here. And this picture also shows us the acting mechanism. So it was oxidation-assisted crack initiation. So the oxides which were formed on the surface at higher temperatures were easily cracked at lower temperatures with the tensile stress field, which is the reason why we had so many cracks at the surface. And this feature is actually also typical for out-of-phase tests in general. And we see that the cracks, there were many of them, and they were running approximately perpendicular to the surface and were short and shallow. So the lifetime was generally governed by propagation of the principal crack, not those small ones. Yeah, so here is how the structure looks like after out-of-phase tests. And we see that obviously thanks to the longer exposure at high temperature, there were more of those particles nucleated. And this time not only at the grain boundaries, but also at subgrain boundaries, dislocation cell walls, and also at oxide precursors. 3 minutes. Okay. So, to conclude my talk, the initial microstructure showed that there was strong texture, which was in regard with the building of the material, the building process of the material. There were fine round defects present in the microstructure. Importantly, no Lego fusion defects were observed. In case of out-of-phase thermomechanical fatigue, the sequence was like this, that the high stresses, which coincides with high temperatures, which exceeded 600 degrees centigrade, which is important for onset of the creep damage in this material, led to nucleation of cavities along grain boundaries, which later grew, coalesced, and as a result we had dominant intergranular damage with massive internal damage. So regarding the microstructure, the dislocation cells were there, they were quite stable still. We had fine round particles still in the microstructure, and these newly precipitated guys, which were elongated, nucleated primarily at the grain boundaries, and were also sharp-edged. Yeah. We also saw that at given temperature range, the in-phase was generally more damaging than out-of-phase. The reason for the radial softening we observed was that due to huge internal damage we had, there was gradual reduction in the cross-section of the material, which led to the decrease of the stress levels we needed to impose the same strain amplitudes. Yeah. In case of out-of-phase thermomechanical fatigue, we had, on the other hand, high stresses at the minimum temperature, which led to the oxidation-assisted crack initiation. We had limited creep damage, which led to mostly transgranular damage with striations at the fracture surface. The microstructure consisted of dislocation cells, which most of them were stable. In some cases they were rearranged, in some cases they were even completely destroyed. We had fine round particles and numerous of fine elongated sharp-edged particles rich in molybdenum, silicon, sometimes also chromium, sometimes, and with lower content of iron and nickel. The nucleation is obviously a function of time. So first of all, we had nucleation at grain boundaries. Later, in out-of-phase tests, since they are longer, we also had nucleation at subgrain boundaries, cellular walls, and oxide particles. Yeah, I suppose that these precipitates, onset of the nucleation of these precipitates, was also the reason why the cyclic stress response saturated, and in some case, in case of high strain amplitudes, even led to the hardening in case of out-of-phase tests. There are several candidates which are considered in the literature in similar cases. These are carbides, silicates, phosphites, sigma phase, whatever. I guess it's ferrite, but it needs some further study. Regarding the influence of the building direction, can I just finish the sentence? We saw that the horizontal building direction was linked with higher stresses, which is apparently caused by not huge, but a higher amount of grain boundaries in the loading direction, which is the cause of higher all-phase strengthening. We also saw higher sensitivity to intergranular cracking, which is quite obvious since if we have cracks like this and we load it like this, it's easier to hold, right? So that's it. I thank you for your attention, and if you've got any questions.